So I will show you, and we will discuss why it is important to have polarized nuclei. The suggestion was to use and to study decay of cobalt 60 into nickel 60 plus electron and plus electron antineutrino. The point is this cobalt has a big spin. The spin of cobalt is 5. And so it is easy to polarize cobalt. It has big spin, so of course you need to use magnetic field to polarize it. It's useful. Now, nickel has the spin 4. So the idea is to study angular distribution of electrons from this decay. So you have cobalt polarized. Of course, it's not 100% polarized, so always there is some depolarization, but mostly it's polarized, which means that there's some rotation in this plane, in horizontal plane, in this direction, if we have the spin directed in such a way. It's cobalt spin. And then what shows up is electron after decay from this process. Theta is the angle between a vector of spin, of polarization of cobalt, and momentum of electron. And so the idea is to study angular dependence and to see if it will be isotropic or the same in up and down directions, or it will be some asymmetry. So that's the idea, to look for asymmetry of emission of electrons from cobalt decay. Now, why asymmetry is indication of parity violation. So search for up-down asymmetry. So why up-down asymmetry is signature of parity violation, although we have still some direction here in the problem. So let me repeat one point which we have discussed already. We have initial state, which is spin of cobalt. But remember, spin has tricky meaning. Spin, just matter of our convention. What has a physical meaning? That we deal with rotation in the plane which is horizontal, and therefore this rotation is symmetric with respect to up and down. So this is P invariant. And of course it is also reflected that under P transformation spin doesn't change. Okay? So direction of spin is just reflecting the fact if rotation occurs in this way or in this way. But in any case, the situation is symmetric with respect to up and down. Agree? Okay. So this is initial state, which is P invariant. And final state is that we have electrons which are flying in general in all the directions. So this is P electron, and in particular in this direction and in this one. So here we deal with up down, and if number of electrons in this direction differs from number of electrons in this direction. Or if you want, you can even integrate over theta, right? So this is the same theta. Integrate over theta and compare the number of events with electrons flying up and down. So if you would observe that number of events with theta is not equal to number of events with pi minus theta, then you certainly violate up-down asymmetry. And so this is p non-symmetric state. Agree? If we have invariant, p invariant, which actually is transformed to p non-invariant, this means that the Hamiltonian, which is responsible for such a transition, should break parity. Okay? So what's important here that initial state is p invariant. Final is not, and if you find that it is not invariant, that means that the Hamiltonian of the theory is not p invariant. Now, why polarization is important? Polarization is important to visualize this asymmetry, because if you would have, for instance, polarization in this direction, and you observe that the number of electrons down is bigger than the number of electrons up, you will see asymmetry. However, if you also have such a situation, then you will see that number of events here will be different from number of events up. And when you sum up, you will kind of hide parity violation effects. So, polarization is needed to visualize p violation effects. So it doesn't mean that if you have unpolarized nuclei that there is no p violation, but you just do not see because you kind of edged the fact and hide in this fact. Okay? Now let us develop a little bit theory. So we need to start with some Hamiltonian. Hamiltonian of weak interactions. And make computations of rate of decay and it is function of kinematical variables, so it's function of momentum of cobalt, spin of cobalt in general, momentum of electron, spin of electron, and also neutrino. You can also use, in general, it depends also on momentum and polarization of neutrinos. Okay? So it's always, eventually we are coming to the rate, which is function of kinematical variables of external particles. Actually, we can obtain dependence of gamma on these kinematical variables, again, without any real computations. So we can use Lorentz invariance. Which tells us that gamma should depend on scalar products of these vectors, right? So that is what can be Lorentz invariant. Should depend on scalar products of vectors. So which vectors do we have here? It's written. And so we can construct several scalar products. We can take momentum of electron and multiply by spin of cobalt. We can take momentum of electron and multiply our spin of electron. We can take momentum of cobalt and multiply onto momentum of electrons. And we can construct even more if we will use a momenta of neutrinos. Now, of course, it's one needs to consider in general 4 vector products, right? But 4 vector products means that you have product of energies and products of momenta. So eventually it also will contain such a scalar product. Okay? Now, what are properties of these combinations under P? Under P transformations, this change the sign, right? That's not invariant. So it's P non-invariant because we have spin here which doesn't change under P, and this momentum changes the sign. The same as here, and this is P invariant as a product of 2 momenta. Both change the sign. So this is P invariant and these 2 P non-invariant. Well, we are assuming that cobalt is at rest, so that P cobalt is 0. What is here is nothing but polarization of spin of electron on the momentum of electron. This is helicity. So it's difficult to measure. You need to measure polarization of electron and then projection of spin onto momentum. So it's just experimentally not reliable here. It's not used. So the only what is left is this scalar product. And now we can write in general the decay rate as sum A times B multiplied by PE multiplied by SE, by S cobalt. So if P is conserved, so if P is conserved, then B should be 0. Because this combination changes the sign, this product, under P transformations. Presence of such a term is indication of P violation. So that's P violating term. This is P violating term in gamma. So this expression expression for gamma can be written as A 1 plus alpha, and alpha depends on, let me put here GA, and polarization are multiplied by cosine theta, where theta just comes from here. So theta is the angle between polarization of cobalt and momentum of electron. So this is the angle which we have introduced already. So this is theta. Now alpha is the function of level of polarization, degree of polarization, and GA is our famous constant, which actually gives a mixture of axial vector current in our general total current. If GA is 0, then there is no axial vector current, and then Hamiltonian is P invariant. And if GA is 0, then this alpha should be 0 also. Okay? So, appearance of this term clearly produces up-down asymmetry, because for up-flying electrons, this is positive, and for down-flying electrons, it is negative. Right? So, which means that you have one, for up direction, you will have one sign of this term, and for another direction, you have another sign. And therefore, gamma up will not be equal to gamma down. So that's down. And this is nothing but pi minus theta. Now let me say a few words about the experiment. So the experiment has been performed in 1957 by C.S. Wu, Madame Wu, did this experiment, and she precisely measured the distribution of produced electrons. What she has found, that for spin of the cobalt up, more electrons are in down direction than in up direction. So here's more electrons. So clearly observing asymmetry, and therefore alpha should be negative, right? And she measured that alpha is minus 0.7. So that gives you the measure of asymmetry up and down in this experiment. Now, alpha is the function of GA and polarization of cobalt, and therefore to extract GA you need to measure what is the level of polarization. The polarization has been measured because in some cases final nuclear nickel 60 was in excited state. So, and it was the excitation with emission of gamma. And what she did, she measured polarization of gammas, angular distribution of gammas. From this decay. And that eventually allowed to determine what was polarization of initial cobalt. Knowing this polarization, one can find what is Ga, and what she has found is this Ga is approximately 1.2. The quantity which we have already used from the beginning, essentially, of the course. So let me again repeat. Polarization was needed to determine alpha. Once you know alpha, so you measure polarization and then you determine what is this Ga. That has been found by studying angular distribution of gammas appearing from nickel decay. So this is the story with establishing of parity violation. Questions?
I have a question. Can you hear me?
Yeah.
How did you measure the polarization of cobalt?
Okay, so that story which even I can tell you immediately. This is kinematics, essentially. And what you see here is that you have cobalt, and then gammas are going. Apart from electron, there are gammas which appear from cobalt. And then measuring angular distribution of these gammas, you can say what is polarization of cobalt. Now let me show you some pictures. So here you see Li and Yang, and you have also the same things, right? Here is Madame Wu and Pauli, and this is Madame Wu with her experiment. And so you see here the device. And this is what essentially we discussed, magnetic field, polarization of cobalt nuclei, and then electrons, which is certainly asymmetric, more coming in this direction than in upper direction. So that's a little bit more about parity violation. Again, so you have this cobalt in the magnetic field. Okay? Look at these pictures. Okay? More questions? By the way, it was even simpler way to establish parity violation. A few years ago, it was a conference on history of neutrinos, and then there were people who actually studied muon decay, as muon decay is also, driven by weak Hamiltonian of weak interactions, and in fact, angular distribution of electrons from muon decay, angular and also energy distribution of electrons depends on the structure of the Hamiltonian. So the shape is different for different structures, Lorentz structures, and just measuring energy distribution. Actually, already data even existed, so just people didn't look carefully at the data for muon decay into electron and to neutrino. Again, measuring energy dependence of this decay, you can establish what is Lorentz structure of currents. So they could be on first. Essentially in 56, they could look at the data or refine experimental results and already conclude that parity is violated. And actually in all the decays which are due to weak interactions, parity is violated. Also in scattering. Nowadays it's everywhere you can see effects of parity violation. Everywhere in weak interactions, of course. So what I need to further discussion and we will discuss mostly CP violation. I need still to say or summarize the results on charge conjugation or C transformation. So we discussed P transformations. Now let me remind, because I know that you have already studied this in the course before, so let me say a few words about charge conjugation. So the story here is very much similar to P transformations. What is C transformation? C transformation is introduced as transformation of particle into antiparticle. Why do you want to introduce such a transformation? This is because we have some observations which testify for symmetry between particles and antiparticles, and in particular, the mass of the particle equals mass of antiparticle, and equalities of masses is manifestation of the symmetry as we discussed. Also, the spin of particle equals to spin of antiparticle. So there is a good reason to introduce such a transformation and explore if our theory is invariant or not under C transformations, and what are physical consequences apart from equality of masses which comes from this symmetry. So how the quantities are transformed, different physical quantities. Since particle and antiparticle, they have different sign of the currents, under C transformation, current should go to minus current. And now all four components change the sign in contrast to P transformations. Also, charge change the sign, electric charge change the sign. And actually other charges also change the sign. Now, how fields are transformed? The scalar field under C transformations go to conjugate, and we introduce eta C parameter, which is similar to what we have introduced for usual parity. The difference here that the scalar field is transformed to scalar conjugate. So that's something which is additional in contrast to P transformations. Now for fermionic fields, the transformation law is the following. C, this is some matrix, then Dirac conjugate and transponent. And you can find out what is Dirac conjugate transformation. C here, 4 matrix, 4 by 4, equals I gamma 2 gamma 0. Now, how this is established? This is established to match this condition. Actually, you can find out the transformation, especially this matrix C, in different ways. But one of the ways to use this physical argument and to use that your psi gamma mu psi under C transformation should change the sign, all 4 components, and then we can find what is this matrix C. I will not do this. I hope you did this in the previous courses. Now, for vector fields, like for photon, C transformation is A mu, go to minus A mu. And this is because we want to have covariance of Maxwell equation. Remember, in the Maxwell equation we have delta A equals the current. And therefore, if the current changes the sign, then to have covariance you need to have A mu also changing the sign. So this is for vector fields. You see, you can say, well, I'm not sure that you need to have this introduction. You may try something different. Again, what I was telling you, you can postulate this type of the transformations. You can try to modify and maybe find something interesting. All the people studied already 50 years, I'm not sure that you will find something interesting, but it may still happen. So this is the way how we introduce transformations of different fields. Now let me introduce C parity. So these are C transformations, and now let me tell you about C parity. So C parity is introduced for truly neutral particles. Particles for each, all the charges are zero. Not just electric, but also strangeness is zero, bottom is zero, charm is zero. So all the quantities have zero value. What are these particles? Example is pi0, gamma, photon, Z0, ρ0, meson, and particles like this. So they have all the charges to be zero. So why it is important? This is important that for these particles, look at this law, that will be at the CF. So for these particles, for truly neutral particles, F conjugate is, let me put it like this in F. So there is no antiparticle of pi0 coincides with pi0. So there is no antiparticle here. In contrast to K0, because K0 has a strangeness. And therefore, making conjugation, you change strangeness. But for those, you do not change anything. Now, let us look at this equality. At quantum level, we can write it as C. We can use operator of C transformations. Acting on the field will give eta C, and the field itself, because particle coincides with antiparticle. Right, so this is at quantum level. And the story is the same as before. Now, for truly neutral particle, this equation, or this transformation law, looks like a equation for eigenstates and eigenvalues of the C operator. Okay? So this is the question for eigenstates and eigenvalues of operator C. So transformation law turns out to be equation for eigenstates or eigenvalues. And this is valid for truly neutral particles only. You cannot introduce such as things for particles with some charges because you will have something else here on the right hand side. Now the same you can introduce for photon. And for photon, we know that photon is transformed with minus sign, and therefore eta C for gamma is minus 1. And you see that is eigenvalue, right? And this becomes a characteristic of given particle, right? Not only this. So if you have symmetry of your theory, then this quantity is conserved. As in the case of parity, usual one, eta C is multiplicative quantum number. So if you have system of particles, then you can introduce total C parity, and that will be the product of C parity of all the particles in a given system. Here also there is entanglement with orbital motion. So imagine that you have the system composite system of E plus and E minus, positronium. Right? So this is truly neutral system. However, if you do conjugation under C, you will get E minus and here E plus. They change the places. And therefore, the corresponding wave function may change the sign according to angular momentum of this system. So that also should be taken into account if you compute total C parity of the system of the particles. There's one important consequence of conservation of C parity. Which is so-called Ferret Theorem. Who knows what is this? If someone has heard this, what is Ferret Theorem? Ferret Theorem is telling the following. Suppose you consider the process with gammas. And of course here some charged particles are running which emit these photons. The theorem is saying that if you have odd number of gammas total, and the beginning plus and the end, then the amplitude of this process with odd number is 0. You see what's important? If you don't know this, you start to compute, you take some charged particles, you can produce such a type of a diagram. You start to compute it, got some non-zero results, start to repeat it or check, spend a couple of weeks to compute this diagram. But if you know the symmetry, already in the beginning you can say nothing to compute, it's just 0. It should be 0. Again, if eta C is conserved. Because if you have even number of gammas, you cannot conserve C parity. So, for instance, in this case, initial state has C parity, if this is an S wave. C parity is 1, right? Because you have 2 gammas. Now, in the final state, you have 3 gammas, and therefore C parity is -1. So, for the odd number of gammas, you cannot satisfy C parity conservation. Questions? Okay, so now we change the topic and we will discuss CP symmetry and CP violation. Remember that Kobayashi Maskawa has proposed their mechanism to explain CP violation. Okay, the experimental result which established a CP violation. And this is what we start to discuss. Before this, I want to just to tell you, just today the paper appeared, maybe that will be interesting for you. The paper, which is actually related to K0 system, which we will discuss now. paper which studied decay of K0 meson into pi and 2 neutrinos. And the experiment has the name K2. Neutrinos are not detected, and so what they see just appearance of pi 0. Actually, this is flavor changing neutral current process, right? Because we have strange particle and it's somehow transformed into non-strange particle and emits 2 neutrinos. So the expected rate of this process is extremely strongly suppressed in the standard model. So if you have some deviations from the standard model, then you may expect some observable quantity or rate of this process. I think it's a couple of years ago, maybe it was already, I think 1918, 2018. The experiment has indicated that they see this decay at the level which is much higher than you expect according to the standard model. Oh, it was big excitement, and you know, many people, especially young people, they want to discover something, start to work on this, and invent some new physics to explain the result of the experiment. And I think maybe about 100 papers have been appeared devoted to explanation of this. Just keep in mind this story. And today there is a paper, literally, you know, it's today, right? So what they are saying is they have found some background that they conclude that the number of observed events is statistically consistent with just background. This is very often story. Some anomaly appears, and actually that was called Koto anomaly. And people work on Koto anomaly, and papers are published, you know, it's not just somebody, they published in leading journals. But the end of the story was that it's just background, which experimentalists overlook. So before you start, and so what does it mean? So some spend half a year, for instance, working on this anomaly. Even my former student published paper on this Koto anomaly. But anyway, so that's one of the things. So we will start to discuss now CP invariance and CP violation. First, CP invariance. You will have also exercise related to these CP transformations. Under P transformations, left components of fermions go to right components. And remember, left and right, they are introduced like 1 plus or minus gamma phi F over 2. So this is for right, and this is for left. You can always split the wave function of your fermion on these two parts, left and right. And then you will check that left component under P transformation go to right component, and under C transformations, a left component, right component go to F, C, left. So if you perform two transformations, that is to have CP acting on F left, what you will get is F right C. Now, if you take Lagrangian or Hamiltonian or weak interactions, that it turned out that under CP, Hamiltonian is invariant. So if you do P transformation, the Hamiltonian is not invariant. However, if you do C and P transformation, and you need to take into account that this contains two parts, the first one and then Hermitian conjugate, then you can find that under CP transformation, our Hamiltonians with this V minus A structure of the currents is invariant. And we will have exercise to check this. So it was hoped that although C and P symmetries are not a good symmetries of Hamiltonian, actually under C also this V minus A changed. However, under the product of these two transformations, Hamiltonian is invariant. So CP invariant Hamiltonian. Under CP, HV go to HV. It doesn't change. And people saw that maybe this is a good symmetry of nature. So eventually CP was broken, and now people are discussing that maybe CPT is broken. So everything is broken at some level. So that's kind of now what is behind of many searches. So we can introduce combined transformations, CP transformations, and you can check that our Hamiltonian of weak interactions is invariant under these CP transformations. Good. Now let me discuss how CP violation has been discovered. And that will require more time. So CP violation. So how you would look for CP violation? What are CP violation effects? What you would measure or search for? Well, this is a good question for physicists, right? So there is this symmetry, and you know, maybe there are some CP violation effects. Okay. So again, curiously enough, it was not trivial actually the way how that was discovered. And again, people saw that this CP invariance is a good invariant, good symmetry of the nature. That has been discovered in the system of K0 and K0 bar. So remember, these are mesons with strangeness, so that K0 and K plus, they form isospin doublet. And they have strangeness +1, while K0 bar and K minus, again they form isospin doublet, they have strangeness -1. So K0 and K0 bar are the eigenstates of strong interactions, because strangeness is conserved in strong interaction. And so these states are eigenstates of strong interaction. Eigenstates are with definite strangeness. So it states with definite strangeness. And therefore, in the strong interaction processes, it is these states which are produced. For instance, if you have collision of pi minus with proton, what you produce is This is one of the channels, lambda 0 plus K0, so that the strangeness is conserved, but the states which you are producing are these K0. So this is K0 what appears here. And lambda is lambda hyperon. Or you may have transition reaction when you have pi plus proton. You go to K0 bar plus K plus proton. And again, strangeness is conserved. You see these particles appear in the pair as well as here. And what appears is particles with definite strangeness. Now let us study properties of K mesons, of K0. It's a little bit boring, but you will see that something very non-trivial appears from this boring analysis. So we are discussing C and P properties of K0 and K0 bar. So if you apply C transformations onto K0, what we will get? So what is the state which appears when I act by C operator onto K0?
K0 bar.
Right, so it's K0 bar. Now, if you act by C onto K0 bar, what you will get?
K0.
Right. Boring, right? So that's trivial. Now let us try with P transformations. If you act by P onto K0, what you will get? Remember, K0, they are in the same octet with pions, right? So pions are pseudo scalars, which means that under P transformations, pions change the sign, and the same is for K meson. So K meson is pseudo scalar, and therefore in change of the sign. Okay? Now, if you add by P, by this operator, onto K0 bar, what you will get?
It's not the same, minus?
Yeah, so you will get K0 bar. Still boring, right? And this is the way to Nobel Prize to grade this kind, not even one, as two experimentalists and then theoreticians who explain this, got the Nobel Prizes. And this is not a joke. The ICTP is very important, actually. Baryogenesis, baryon-asymmetry of the universe requires the CP violation. Now, let's take CP, combined transformation. So how this K0 is transformed. So if we act both P and C, what do we get here?
Minus K0 bar.
Good. K0 bar, right? Because you have C which transforms K0. Now the same is for K0 bar. What you will get? Yeah. Even more boring, no? Now the trick, which is actually I'm using here, and it's useful to use this trick in many other circumstances. Remember this. Now let's try to introduce the states with definite CP properties. So we can introduce state K1, which is the combination of 1 square root of 2, this is for normalization, K0 minus K0 bar. And I will introduce K2, which is 1 square root of 2, K0 plus K0 bar. So the sign is here, these two are orthogonal combinations of this. Now what are CP properties of these states? Now CP acting on K1 gives me what? Using these properties under CP of K0 and K0 bar. So what we will get for K1 transformations? How this is transformed under CP?
It's the same K1.
Yeah. It's already more interesting because now you see we have K1 and K1 here, so which means that K1 is a combination which has definite CP properties. So now let's take K2. How this is transformed?
Minus K2.
Right, so that's minus K2. Now it becomes more interesting. So these two equations can be considered now as equations for eigenstates and eigenvalues of operator CP. And we can introduce CP parity, right? Which is eigenvalue of this equation, and therefore at the CP of K1 is 1, and at the CP of K2 is minus 1. So here we deal with mixing of K0 bosons, right? And combinations of K0 and K0 bar have definite properties with respect to CP. So the states K0 and K0 bar are the eigenstates of strong interactions, so to say. Remember, weak interactions also break strangeness. These states, K1 and K2, are good for weak interactions. So to say they are eigenstates of weak interactions. And again, we have mixing when we have two sets of the states which are related by mixing. K0, K0 bar are the eigenstates of weak interactions of strangeness. K1 and K2 are the eigenstates of weak interactions. So just for you to remember better. So we have K0, K0 bar. So the eigenstates of strong interactions or strangeness and then we have this K1 and K2. These are the states with definite CP properties. And so if weak interactions have this CP symmetry, so they are eigenstates of weak interactions. Okay? Now let us explore the decays of K mesons. K mesons can decay in general into 2 pions or 3 pions. We already met this. Now let us consider the system of 2 pions. Okay, let me write it. K in general can have decay into 2 pions and can have decay into 3 pions. So let us explore the properties of 2 pion system. So first let's take 2 pi zeros. Pi 0, pi 0. So what is CP property of this combination? Let me remind that pi 0 has the spin 0, it has minus usual parity and plus C parity. Remember, pi 0 has decay mode into gamma gamma, and since each of these have C parity minus 1, then C parity of pi 0 is plus, so you can find in the table of particles, this is labeled for pi 0. Therefore, these CP transformations give us just plus pi 0, pi 0. Because we have just square of everything, right? We have here. Internal parity of pi 0 is minus, but we have 2, and therefore we will have plus 1. Now C parities are plus 1. Spin is 0 since they appear from the particle with spin 0. And therefore CP parity here is 1. Agree? Now we can consider also CP of charge pions. CP of pi plus, pi minus. What is this? So it's given by eta parity square of each of the pions. It has also minus 1 L due to exchange of pi plus and pi minus. Both parity and CP interchange of pi plus and pi minus. So we have this system, pi plus and pi minus. But L is 0 anyway, so that gives us anyway 1. And then C parities we do not introduce. We introduce C parity of this state. Bottom line, that gives us pi plus, pi minus. And therefore again, the CP parity of 2 pions, pi plus, pi minus, is 1. Now let us consider 3 pion system. I will not repeat the arguments, but the key parameter here is internal parity of pion. So essentially that will be given by eta pion Q. We have 3 pions here. And the rest is just because orbital moment is 0, so that what we will have here again, pi 0, pi 0, pi 0. And now at the CP of 3 pi zeros is minus 1. It's just because we have 3 pions here. And less trivial, but again you can convince yourself that CP of pi plus, pi minus, pi 0 with 3 pions It has this feature that we have pi plus and pi minus. And under C and P, again, there's double permutation. And this factor also exists here. And therefore, what we get here, minus pi plus, pi minus, pi 0. And therefore, Cp of this system will be again minus 1. So bottom line, the system of 2 pions independently on charge, which originate from K0, have Cp parity plus 1. 3 pions have Cp parity minus 1. And probably I will just say a few words and then I may spend tomorrow, because tomorrow we will have checks. I don't want to take time today. I will probably discuss the experiment tomorrow. So now we come back to our K1 and K2. K1 has Cp parity plus 1. And therefore, if Cp is conserved, this can decay only into 2 pions. So this has 1. In contrast, K2 with Cp parity minus 1 can decay only in 3 pions. This has Cp parity also minus 1. Again, if Cp is good symmetry of the theory, that K1 can decay only into 2 pions and K2 can decay only in 3 pions. What has been observed is that also K2 decays into 2 pions. And therefore, Cp is broken, because here we have Cp parity minus 1, and Cp parity of these pions, 2 pions, is plus 1. So here we have Cp violation. Bottom line, observations of K2 decay into 2 pions was discovery of Cp violation. And you see how many consequences. So Cp was observed, then Kobayashi and Maskarov introduced the third generation of quarks to explain this. And then we introduced also the third generation of leptons. And then we checked that actually Cp is due to mixing or in 3 generations. I will discuss the experiment tomorrow. So I'll spend maybe 10 minutes from checks of the exercises to tell you about this experiment. Questions? Clear?
Professor?
Yeah?
One question. I mean, when we define K1 and K2 as conventional, K0 and K0 bar.
Yeah?
Okay. And now we are, experimentally, how they differ the K1 and K2?
Oh, so that's what I will discuss. This is non-trivial, right? So that's why experimentalists got a Nobel Prize for this. So how you get the beam of, right? So that's your question. So wait for tomorrow. I don't want to say this in advance. But you can think how to do this, by the way. I can ask you questions. Can you imagine how we can create the beam of K1 or K2? right? Because you have strong interactions and you produce K0 and K0 bar in strong interactions, right? But then you need to manage to have the beam, pure beam of say K2, right? And then to see if it decays or not into 3 pi. Yeah, that's non-trivial. Well, it's trivial when I will show you. You'll say, okay, that's trivial. As usual, right? So after all, you know, everything is trivial. Almost, no? Almost trivial. More questions. You see, we are doing well. We studied the parity violation now, approaching CP violation. We all violated almost everything, right? So what else we should violate? CPT, right? The Lorentz invariance. Lorentz invariance, yeah, and CPT. And you know how many people are working on this? Because, you know, now, so in the early days, people said, okay, nature should be quite symmetric, very symmetric. And then there is no question, you know, if everything is symmetric, then okay, it's symmetric, right? If you have violation of symmetry, then you start to think, that's a problem, right? And you need to explain why it is violated. You are not asking question why it is symmetric. That's fine, you know, it's nice, fine. You start to ask questions when you see violation of something. I said that something is, you know, nasty, you know, one needs to do something about that. And nowadays people are working on Lorentz symmetry violation and CPT. Even I have paper on CPT violation. But anyway, that's even Pauli principle. People are discussing maybe Pauli principle is not kind of perfect. There is something. Okay? So then see you tomorrow. And again, I will start tomorrow spending 10 minutes, you know, answering your question about how to create beam of K2 mesons. Okay.